Dear students, in this video on current electricity, we will study about Kirchhoff's rules and numerical problems based on them. So starting with the first law, it is also called Junction Rule. So the algebraic sum of electric currents at a junction in any electrical network is always 0. It means the sum of incoming currents and sum of outgoing currents must be equal at a junction, you see. If we take incoming currents as positive like I1 and I4 and outgoing currents as negative I2, I3 and I5, then their algebraic sum will be 0, or we can say that sum of incoming currents is equal to sum of outgoing currents. Now, this happens because charges cannot accumulate at a junction, right? So the number of charges reaching a junction must be equal to the number of charges leaving the junction, and it is based on the law of conservation of charges, right? So the next one is voltage law of loop rule. Okay. The algebraic sum of all the potential drops along any closed path in an electrical network is always 0. That means along a closed path, the net potential drop is always 0, right? So let us look at one example here. We have a network like this containing two cells E1, E2, resistances R1, R2, R3. Now here, okay, if you look at this point A, then current from E1 is reaching here as I1, current from E2 reaching here as I2, and at point A they are adding up, and current I1 plus I2 is leaving the junction through R2. So we have used junction rule here. Now at point C, I2 goes back to E2 and I1 goes back to E1. See, at this point I1 goes back to E1 and I2 goes back to E2, right? Now if we want to apply this Kirchhoff's loop rule, we must understand certain sign conventions. So let us discuss the sign conventions first. See, while moving in a circuit, the rise of potential is taken as positive. That means agar potential badhega, it will be taken as positive, and fall of potential is taken as negative. If potential is decreasing, it will be taken as negative. Very important, you must remember that. And this law is based on law of conservation of energy. So let us see how we use this law in these mesh. So the first thing first, let us place the higher potential points and lower potential points. So for a cell, this positive electrode is higher potential, negative electrode is lower potential. Now current always flows from higher potential to lower potential. So for current through R1 and for current through R2, higher potential to lower potential. For R3, higher to lower potential. For E2, negative potential is lower and positive potential is higher, right? Now, in a closed path, you can move along clockwise and along anti-clockwise. That is your choice. So if you look at the equations now, while moving from point A along B, C, D, like in loop A, B, C, A, along this path. When you move, you are moving for cell E1 from higher potential to lower potential. So E1 is negative. Through this resistance R, we are moving from lower potential to higher potential, rise of potential. So plus I1 R1. And for this resistance R2, we are moving from lower potential to higher potential. So it is I1 plus I2 into R2. You know, potential drop across a resistance is equal to current into resistance, Ohm's law. So we are using that, and in this way we have got this first equation, a long loop A, B, C, A, right? So equation this one. For the second equation, let us look at the loop once again. See, let us mark positive, negative first. So for resistance R2, current is flowing from higher potential to lower potential. For R3 also, current is flowing from higher potential to lower potential. For E2, negative terminal is negative and positive terminal is positive, higher potential. And when you are moving along ACDA in clockwise direction, see, for R2 you are moving from higher potential to lower potential. So the potential difference is minus I1 plus I2 into R2. For R3 we move from higher potential to lower potential. Again fall of potential. So minus I2 R3. For the cell E2 we are moving from lower potential to higher potential. So we will get plus E2, and in this way we get this equation, right? So that's how we write equations using Kirchhoff's rule. Now we can take one more mesh along this direction A, B, C, D, and when we do so we can neglect this arm along the diagonal. So we must learn to solve numerical problems and we can apply them. Before moving to numerical problems, let us do this special arrangement of resistances, which is called Wheatstonebridge. If we have four resistances P, Q, R, S connected to external cell as E, and we have a resistance or a galvanometer along this arm BD, then this arrangement is called Wheatstone bridge. So you can see it is a bridge-like structure. Now, the current starting from cell E is I, and at point A it gets divided in two parts as I1 and I2, right? Then at point B it again divides in two parts. You can see current through galvanometer is Ig and the remaining current is I1 minus Ig, right? And at point D, see, this I2 and Ig add up and you get I2 plus Ig. At this point C, this current and this current, they are adding up and you will get I1 plus I2. So from this cell, current I1 plus I2 started. See, I is equal to I1 plus I2 and current I1 plus I2 returns, right? So the equation is circuit is complete, and using Kirchhoff's rule for different loops here. So let us choose this loop A, B, D, A. For this, let us show the higher potential and lower potential. So for P, this current I1 is passing along AB, so higher potential to lower potential. For galvanometer, higher potential to lower potential. For resistance R, this is higher potential, this is lower potential. Remember, current always flows from higher potential to lower potential, right? So if you start at point A, then for resistance P, the current is flowing from higher to lower, which is fall of potential, so minus I1P. For galvanometer, again fall of potential, minus Ig into G. For resistance R, you are moving from lower potential to higher potential, so it is rise of potential, so positive. So in this way you have got this equation, and if you move to the second loop, which is B, C, D, A, and for that loop again we can show the sign convention here. this end is positive, current is flowing from higher potential to lower potential. For this one, this end is positive and this end is negative. For galvanometer, this end is positive and this end is negative. Remember that current always flows from higher potential to lower potential. So while moving along this direction from B to C, we are facing a fall of potential, so it is going to be negative. So we will get minus I2 minus I1 minus G into Q. For moving along this direction, we are moving from lower to higher potential, so we will get a positive sign plus I2 plus Ig into S. And while moving along this direction, again we are moving from lower to higher potential, so rise of potential, a positive term. So in this way the mesh is complete and we get these two equations here. Now, when current through this galvanometer is 0, or when this point B and point D are at the same potential, then this Wheatstonebridge is said to be balanced. Now, for a balanced Wheatstonebridge, see Ig is 0. So when we put Ig 0 in this equation as well as in this equation, we will get the relations like I1P is equal to I2R and I1Q is equal to I2S, and divide this equation by this equation, you will get this relation as P upon Q is equal to R upon S. That means P upon Q is equal to R upon S. So if we have a Wheatstonebridge where this ratio of these two is equal to these two, then we say that the Wheatstonebridge is balanced and no current will pass through this arm and we can totally neglect it, right? So now let us move to numerical problem. So let us look at this numerical problem. Two cells of 4 volt 2 ohm and 2 volt 2 ohm are connected in parallel in such a way that they send current through an external resistance of 9 ohm along the same direction. Now the first part is draw the circuit diagram. So you must understand it first that the cells 4 volt and 2 volt with given resistances are connected in parallel. First thing, and they are sending current along the same direction through external resistance 9 ohm. So understanding this, you should be able to draw the circuit diagram. And look at the circuit diagram, you see. Here we have this 4 volt battery with 2 ohm internal resistance, 2 volt battery with 2 ohm internal resistance. They are sending current along the same direction through the external resistance R of 9 ohm, right? So you should be able to draw a circuit diagram. Now after passing through this, when current reaches here, you see the current I2 returns back to this cell, and current I1 returns back to this cell. So you must try to understand the language of question and you can draw the circuit. Now find the current through each arm. That means I have to find current I1 starting from this cell 4 volt and I2 starting from cell of 2 volt and this I1 plus I2 which passes through this 9 ohm resistance. So we will write equations using Kirchhoff's rule for different closed circuits. So let us begin with the first equation. See, in closed loop EFCBE, let us look at EFCBE. EFCBE. This is the closed loop, right? And we are moving along this direction only, right? And we are totally neglecting the outer cell. Okay. So for resistance 9 ohm, we are moving from higher potential to lower potential because current flows from higher potential to lower potential. So the potential difference is minus I1 plus I2 into 9. Fall of potential is taken as negative. Now when you reach through this 2 ohm resistance, you are moving from higher potential to lower potential. Again fall of potential, so minus 2I2. Now when you reach the cell, you are moving from lower potential to higher potential. So rise of potential is taken as plus is equal to 0, right? Now simplifying this equation, you will get these steps, and let this be the first equation from this first loop. In the same way, we'll write two more equations. So circuit once again for your reference. Now in closed loop EFDAE, EFDAE, we are taking this one, and this part is totally neglected. So while doing so, again potential drop across 9 ohm is minus I1 plus I2 into 9 because there is fall of potential. Then when it moves from here through this 2 ohm resistance, you are moving from higher potential to lower potential, fall of potential, so minus 2 I1, and for the cell it is rise of potential, so positive or plus 4 volt, and now the circuit is completed, so it is equal to 0. So total algebraic sum is equal to 0, and simplifying it further, you can see the second equation as 11I1 plus 9I2 is equal to 4. So you are able to write two equations, and we will write one more equation. Now for the third equation, okay, let us choose this loop A, B, C, D, A. A, B, C, D, A. Now for this loop, when we start at, say, we can start at any point. So if I start at this point, then potential drop across this 2 ohm is 2I1. See, minus 2I1 because it is moving from higher potential to lower potential. See, moving clockwise or anti-clockwise is purely your choice, right? Now when you move to the cell, then you are moving from lower potential to higher potential, so plus 4. Now when you are moving along the second cell, you are moving from higher potential to lower potential, fall of potential, minus 2. And when you are moving along this resistance 2 ohm, you are moving from lower potential to higher potential, so there is rise of potential to plus 2I2 is equal to 0. Now you must remember the sign convention, then only you will be able to do it. So open the equation, simplify it, you get I1 minus I2 is equal to 1. From this equation, I2 can be written as I1 minus 1, and we can use this value in previous equations. So let us put this value in equation number 1. So see what we get. Say 9I1 plus 11. Now in place of I2, we have placed I1 minus 1 is equal to 2. Simplify the equation. You get I1 is equal to 13 upon 20 ampere. And then I2 is I1 minus 1. So 13 upon 20 minus 1, that is minus 7 upon 20. Now the significance of this minus sign. Okay. Now if we had taken current along this direction, then the actual current is along this direction, opposite to that. The actual current is opposite to the direction that we have assumed. Okay. And the total current is I1 plus I2, that is 13 upon 20 minus 7 upon 20 is equal to 6 upon 20, and simplifying it we get 3 upon 10 ampere. Okay, so in this way, just by using the Kirchhoff's rules, we can find out current in any segment. See, I'll just take this diagram once again. So if you look at it, this current comes out to be 13 upon 20 ampere. This current is negative, that means this way. So minus 7 upon 20 ampere. And at this point, you see, at this point, one part goes to this arm, one part goes to this arm. The remaining part will be this one, that is 6 upon 20 ampere passing through this one. This is the actual path of the currents followed in this circuit. Okay. So now the next problem, a very good problem and a board problem. So let us try to understand it first. Using Kirchhoff's rule, determine the value of a known resistance R in the circuit. This we have to find out, so that no current flows through 4 ohm resistance. Through this resistance there is no current. I is equal to 0 here. Also find the potential difference between points A and D. We have to find out potential difference between point A and point D. So I hope the question is clear. And let us look at the solution first. See, it is the same circuit. Let us try to look at the direction of current here. See, from this, okay, from this 9 volt battery, this current I1 has started. See, the current I is moving. The same current I is passing through 1 ohm and through this 1 ohm and at this point, and current through this 4 ohm is 0, I is 0. That means the same current I is passing through this path. The same current is passing through R and it is returning back to 9 volt battery. So the 9 volt battery is giving current I, which is taking this route along A, F, D, E, A, and no current is passing through this arm. So I hope this must be clear. Now we will apply Kirchhoff's rule along Kirchhoff's rule along this path as well as along this path, right? One by one. So for this one, you see, positive, negative, positive, negative, positive, negative. You know that current flows from higher potential to lower potential. And for a cell, positive terminal is higher and negative terminal is lower. And this is positive and this is negative. Alright. So if we apply Kirchhoff's rule in A, F, E, B, let's see what we get. Now look at the solution now. We are applying Kirchhoff's rule in this path, and if you start at point A, see, potential drop across this 1 ohm resistance will be equal to minus IR, that is minus I into 1, minus because we are moving from higher potential to lower potential, fall of potential is negative. Similarly for this 1 ohm, minus I into 1, and for 4 ohm current is 0. Then comes the 6 volt battery. For 6 volt battery we are moving from higher potential to lower potential, so it is minus 6. And then we move to this 9 volt battery. We are moving from lower potential to higher potential, so it is positive. So in this way, when we take this full round clockwise, we get this equation, right? Now simplifying it, you get minus 2I plus 3 is equal to 0, or I is equal to 1.5 ampere. So current in the circuit is 1.5 ampere. Okay, and now we will apply Kirchhoff rule in the in BEDCB. BEDCB again clockwise. Alright, so while doing it, you can see that we are moving along this direction, see, clockwise. So for this cells, we are moving from negative to positive, rise of potential. For this 4 ohm, there is no current, so potential difference is 0. For this resistance R, we are moving from higher to lower potential, direction of current is this. And for this 3 volt, higher potential to lower potential. So this for plus 6 volt battery, you will get plus 6. For 4 ohm, we get 0. For resistance R, we get IR. And for the cell of 3 volt, we are moving from higher to lower, that is fall of potential. This is equal to 0. Simplifying it, IR is equal to 3, or R is equal to 3 upon 1.5. You know the value of current is already given, known to you. So R is equal to 2 ohm. Okay. Now we wish to find out potential difference between points A and D. So one thing is clear, that potential at D and E are equal because there is no resistance present here. So we want to find out potential between point A and E now, right? And we know that current always flows from higher potential to lower potential. So VA is greater than VD. Potential at VA is more than potential at D or potential at E, right? So the potential difference will be potential difference across this 1 ohm plus potential difference across this 1 ohm, right? And that VAD is equal to 1 I into 1 plus I into 1, that is equal to 2 into I, and the value of I is already known to you, 1.5. So multiplying it, you get 3 volt. So the potential difference between points A and D is equal to 3 volt. Okay. So by using Kirchhoff's rules, you can solve such problems. Another very good problem. So the question itself is, calculate the current drawn from the cell. Now look at this. Here we have a arrangement like this, where you get 5 ohm, 10 ohm, 20 ohm, 10 ohm, 10 ohm. We have to rearrange the this arrangement to find out the resultant. So let us draw this arm BC as vertical and see what we get. We have taken this point B at this point, see, and the C is here. Okay, the point C here. Right, and then point A here, and between A and B we have 5 ohm resistance here. Between D and B we have 10 ohm resistance. So between D and B we have 10 ohm resistance, and if we bring it down here, between A and C we have 10 ohm resistance, which can be seen here, and between C and D we have 20 ohm resistance, as can be seen in this diagram also. So after rearrangement, we have obtained this Wheatstonebridge with AB as 5 ohm, BD as 10 ohm, AC as 10 ohm, and CD as 20 ohm. Now ratio of this and this, 5 upon 10 is 1 by 2, 10 upon 20 is 1 by 2. That means it is a balanced Wheatstonebridge and no current will pass through this 10 ohm resistance. So this arm BC can be neglected totally, and we are left with just this 5 ohm and 10 ohm in series like this, 10 ohm and 20 ohm in series like this, and then these two series resistances, that is 10 plus 15 and 10 plus 20, they will be in parallel, and we can find out their resultant and then current through it. So let us try to do the solution. So you can see RAB upon RBD, RAB upon RBD, that is 5 upon 10, it is equal to 2, and RAC upon RCD, 10 upon 20 is equal to 2. So it is a balanced Wheatstonebridge, and current will not pass through arm BC, which is this one, 10 ohm, so it can be neglected. So if we take the series combination of this one, that is 5 plus 10 is 15 ohm, and series combination of these two, that is 10 plus 20 is 30 ohm, and then these two are in parallel. So now the parallel combination is R equivalent, that is R1 R2 upon R1 plus R2. So 15 into 20 upon 15 plus 30, 15 into 30 upon 15 plus 30, and you get 10 ohm. So the equivalent resistance of this whole combination is 10 ohm, right? And the cell used is of 5 volt. So the current drawn will be equal to, current I is equal to E upon R. So 5 volt upon 10 ohm, and that is 0.5 ampere. Okay. So you should be able to identify circuits like this, and you should be able to rearrange them. So now this is your NCERT problem. Here again a Wheatstonebridge is given. See, determine the current in each branch of the network as shown in this. But here you have 10 ohm and 5 ohm. So the ratio is 10 upon 5, 2. Here we have 5 ohm and 10 ohm. The ratio is 5 upon 10. That is, this is 1 upon 2 and this is 2. So that means this is not a balanced Wheatstonebridge. And if this is not a balanced Wheatstonebridge, that means through this arm current will be flowing all the time. Okay, and if that is the case, we cannot use the condition for balanced Wheatstonebridge. So P upon Q is equal to R upon S is not applicable here, and we have to use Kirchhoff's rules here for each mesh. So we have drawn it here like the battery is given to be 10 volt. So if current is starting from this battery, it first passes through this 10 ohm resistance, and current passes from higher to lower potential. This current I gets divided here in two parts. One part I1 goes to 10 ohm and I minus I1 goes to 5 ohm, right? At this point B, it gets divided in two parts as Ig passing through 5 ohm and I1 minus Ig passing through 5 ohm here. Again at this point D, the currents are added. You get I minus I1 plus Ig, and at this point the currents are added and this current I is returning back to the cell. Okay. So first you must show all the positive and negative signs showing higher and lower potentials, and you must draw the path followed by the current. So let us write the first equation for ABDA. Now if you look at ABDA, you see, for this path, you see, I1 is moving from higher to lower potential, so it has to be negative. So minus I1 into 10. For this part, when you're moving like this, you're moving from higher to lower potential, so minus I1 Ig into 5. And when you're moving this way, you're moving from lower to higher. That means rise of potential. So positive. So I minus I1 into 5 is equal to 0. So here you see. See. Minus 10 I1 here. Minus 5 Ig, this one. And plus I minus I1 into 5 is equal to 0. So you get the first equation as simplifying minus 3I1 plus I minus Ig is equal to 0. First equation. Now we will write similar equation for the second loop, and then we will write equation for this loop one by one. So for the second loop, in closed loop EADCF, let's get back to this one. See, in this one, in this closed loop EADCFE, we are moving along this direction, starting this way, just neglecting this outer part, everything. So when we do it, for this 10 ohm, the current passing through it is I. So I will, and it is moving from higher potential to lower potential. So you get minus 10I. For this resistance, 5 ohm, you are moving from higher to lower. So again you will get minus I minus I1 into 5. When you move along this direction, you are moving along the fall of potential. So again a negative sign. And when you're returning back, for this cell, it is rise of potential. So it is going to be positive. So keeping all these things in mind, we write the equation, you see. So minus 10I minus I minus I1 into 5 minus I minus I1 plus Ig into 10 plus 10 is equal to 0. Simplifying it, we get this equation, equation number 2. Okay. And now we are considering closed loop BCDB, the other triangle. And when we write it for other triangle, just look at it, this the other triangle also. Here in this triangle, again we are moving clockwise. So for 5 ohm, we are moving along the direction of current, fall of potential, so negative term. When we move this way, we are moving opposite to direction of current, rise of potential to positive. When you're moving like this, we are moving opposite to direction of current, that is rise of potential, again positive. So first term is negative, the other two are positive. So in closed loop BCDA, you get minus I1 minus Ig into 5 plus I minus I1 plus Ig into 10 plus 5Ig is equal to 0. Simplifying it, we get this much. And then solving these three equations, we get I is equal to 10 upon 17 ampere, I1 is equal to 4 upon 17 ampere, and Ig is equal to minus 2 upon 17 ampere. So you already know how to solve equations. You must learn to make equations using Kirchhoff's rule. And this again is a NCERT problem only. So let us look at it. A very good problem. Here. A battery of 10 volt and negligible internal resistance is connected across diagonally opposite corners of a cubical network, connecting 12 resistances, each of resistance 1 ohm, as shown in this figure. Determine the equivalent resistance of the network and current along each edge of the cube. Okay, so here we have a cube with each edge having 1 ohm of resistance, right? So this is a very symmetrical cube, and diametrically opposite points are connected to a battery of 10 volt. So here symmetry is going to help us a lot, right? So from this cell or battery, when current starts, then at this point A, it is dividing in 3 parts. See, along AA dash, along AB, and along AD. these three paths are taken. And due to symmetry, all three paths will carry equal currents. So for the sake of simplicity, we have taken the current drawn from the battery as 3 ampere. So 1 ampere goes along AA dash, along 3I, and I goes along AA dash, I goes along AD, and I goes along AB. Okay. Now at point B, the current divides in two equal parts, right? So due to symmetry, equal division, so BB dash will get I by 2 and BC will also get I by 2, right? Now at this point, the similar division will take place at this point. So I by 2 will come from here and I by 2 will come from here, and they combine together to give I, right? And from here also I by 2 will come from this side, and they 2 will give you I, and this I by 2 and I by 2 coming from here, and they will be meeting and giving I. So at this point C, again 3I current will be returned back to the cell. So you must understand this division of current, right? And we can choose a closed loop which consists of this cell E, the point A, B, C, C dash, and back to this, the outer path only. We are just not considering the inner part, right? And using this, we can write the equation, Kirchhoff's rules. So Kirchhoff's rule. Okay, let the current drawn from the cell be 3I. Now due to symmetry at point A, the current is divided equally among the three paths. At B, the current divides equally and BB dash. Or applying Kirchhoff's rule, you will get minus I into 1 minus I by 2 into 1 minus I into 1 plus 10 is equal to 0. Okay, let us get back to this figure once again. See, if we are moving like this, you see, potential drop from higher to lower. So you'll get minus I into 1. Resistance R is equal to 1 ohm. When you move along this direction, then minus I by 2 into 1. When you move along this direction, again I into 1. And when you return back, for the cell, it is for lower potential to higher potential, so plus 10. Okay. So that's how the equation becomes this much: minus I into 1 minus I by 2 into 1 minus I into 1 plus 10 is equal to 0. Simplifying, you get 5I by 2 is equal to 10, or I is equal to 4 ampere. The I value of I is 4, but the total current drawn from the cell is 3I. Okay, so the total current drawn from the cell is the 12 ampere, 3 into 4, and equivalent resistance will be E upon 3I, means total EMF upon total current, right? That is 10 upon 12, and you get 5 upon 6 ohm. So equivalent resistance of the given configuration is 5 upon 6 ohm. Thank you for watching this video.